All right, we are going to take a look at Chapter 12, the laws of thermodynamics. So, in this section, we're going to learn a bit about PV diagrams, which come up a lot on the AP exam. The first law of thermodynamics, the second law of thermodynamics, entropy, and ultimately the net change in energy for a cyclical process. Those are some of the things we're going to be taking a look at in this section. You're going to need to be able to calculate the area under the curve for a PV diagram. We're going to relate the first law of thermodynamics to conservation of energy, because ultimately the first law is really just a restating of conservation of energy, and you'll see what I mean. We're going to calculate the efficiency of a heat engine as well as the maximum possible efficiency of a theoretical heat engine, because even theoretically, they're typically not even close to 100% efficient. But you'll see what I'm talking about. We're going to calculate the work done by a heat engine, and we're also going to analyze a system in terms of entropy. First, if we do work on a gas, that means we have to squeeze it because, again, work is force times the displacement. So if we try to exert a force but we don't make the gas move at all, we didn't do any work. So we have to change the volume. If we compact the volume of a gas, we do work on the gas. But if we allow the gas to expand, then the gas itself is doing work, which would be considered negative work because we do positive work on the gas. And when it does work, it would be taking energy out of the gas. So it would be considered negative work when we start talking about energy. PV diagrams, these are pressure versus volume diagrams, can be exceptionally helpful in understanding what is happening with a gas. So you can see that ultimately, if we're trying to find the area in the curve, that's P times V. And that's going to basically help us find the work that is done on the gas, because ultimately pressure times volume, work is equal to the area. When we work out the units, we would get joules in that situation. So the PV diagrams are really good in letting us know how much work is either done on or done by a gas. Now, we are not going to be dealing with a lot of curvy stuff in terms of finding area because, again, that would involve calculus. But when you get to calc-based physics, you would easily be able to do that. We're going to be sticking with some more basic areas under the curve without having to deal with the calculus. All right, we learned about the ideal gas law previously, the PV equals nRT, but now we're going to talk a little bit more about some different thermal processes that we can do messing with this equation, ultimately changing the other variables while keeping one constant. So an isobaric process is one where the first letter there, the P, stays constant. We're going to keep the pressure constant on the gas. Isovolumetric, sometimes called isochoric, you can see those in different ways depending on the textbook or website you're looking at, is a process done while maintaining a constant volume. Isothermal means that we're going to be messing with the pressure and volume while keeping the temperature the same. And then we also have adiabatic. These tend to be very, very quick compressions or expansions, like you would find in the engine of a car, where there's no energy that leaks out of it. So the gas might heat up, but ultimately temperature or heat energy is not brought into or out of the system. So an isobaric process, as I said, is one where we're going to be maintaining a constant pressure on the system. So if the piston here is weighted down, if I increase the temperature by heating it up, I'm going to increase the volume while keeping that pressure constant. Isovolumetric, you'll find that a lot when you have gas cylinders because they're usually made out of metal. So there's a very particular amount of volume that the gas is going to take up. So when we either add heat or take heat away or mess with the number of moles of gas that are in there, we're keeping the volume constant. Isothermal is we are going to keep the heat or the temperature of the gas constant. So these tend to take quite a bit of time because if you were just to quickly compact the gas, you would increase the temperature of that gas. So you have to do this very, very slowly and allow the extra temperature that would occur in the gas, so the extra energy in the gas for heat energy, you have to allow that to dissipate out of the system in an isothermal process. And again, adiabatic is very, very quick, where in this particular thing, you can see the syringe, the person presses down really fast, so the gas heats up so much because of the decreasing volume in such a short period of time that it's enough to cause the little bit of, you can see the white little poof ball there, it's usually a little bit of cotton, to actually catch on fire because the temperature increased so fast because the temperature of the gas did not have the ability to escape out of the container because the temperature increased too quickly. So on a PV diagram, you can see these blue lines are very, very helpful. It's very good to know what these look like. So an isothermal reaction occurs upon one of those sort of curved lines there. Those are called isotherms, where depending on the pressure and volume. They can, so you see the pressure volume relationship at constant temperatures there. Those are all those light blue lines. So an isobaric is the top line, where it's just horizontal line. That's an isobaric process because the pressure remains constant. Isochoric or isovolumetric is a vertical line because, again, the volume is constant. An isothermal reaction takes place along one of those curves, and then an adiabatic jumps from one isotherm to the other, where we're going to be heating things up. And again, those typically happen very quickly, like inside of an internal combustion engine. The first law of thermodynamics is really just a conservation of energy. So the change in energy, which is delta U, equals the amount of heat energy, Q, that you put into or take out of a system, plus the amount of work that you do on or by a system, which again basically just means if I take heat energy and I put it in there, if I do work and do more energy in there, that's going to change the energy the exact same amount. The energy doesn't get created or destroyed. It doesn't disappear out into nothingness. We can use conservation of energy in thermal processes. We have a cyclical process. This can happen in the real world. So a gas can go from point A to point B to point C and then back when we do some work on this thing to just get a repeat of a system. Again, think maybe like internal combustion engine, where you get the same process happening over and over and over and over and over and over again rapidly to get a particular outcome that you're looking for. And the net change in energy in a cyclical process is zero. Because ultimately, we get right back to where we started. So that'd be equivalent of dropping a ball onto the ground. It's got to have potential energy, gain kinetic as it falls, bounces, and pops back up. If it gets to the same height, all that energy goes back to where it was. We have no net change in energy when you have a cyclical process. Heat engine, as I said, is one of the most common ways, or most common things that you're going to find in physics and engineering, in use in thermodynamics and all of these different processes where we're going to heat up a gas, get it to move some things. So we're moving energy around with heat to cause motion, to get a desired outcome, to get a machine to do work for us. So really simply, drawing of a heat engine on the left side, you're going to have a hot area. That hot area, the heat's going to flow into the heat engine. You're going to get some of that out as work. So some of that heat energy is going to be turned into work, and some of it is going to be wasted and sent to a cold reservoir. And you can see the equations for efficiency on that picture. But the heat energy is going to be equal to the amount of work. So the energy flowing out of the hot reservoir has to equal the amount of work that gets done. And anything that doesn't get used as work is waste heat energy sent to the cold reservoir. So the second law of thermodynamics says heat will not flow spontaneously from a colder body to a warmer body. This is why you don't find, if you take a glass of water and you toss ice cubes into it, what happens? The ice starts to melt because the heat energy from the warmer water is going to go into the ice, melting the ice. What you don't find is that the ice cubes get bigger inside of your glass of water. That doesn't happen. Why? Because the ice cube can't leach away cold energy. It doesn't really work. And the ice cubes don't give up their heat energy to the water to get colder and colder. So heat is always going to move from the hotter reservoir to the colder reservoir. And also, because heat cannot be, basically heat cannot be used perfectly. You're always going to have some waste. So heat cannot be transformed completely into mechanical work. So there is no such thing as a perpetual motion machine or perfectly efficient engine. So entropy. Entropy is really kind of a cool way to take a look at a system. It has to do with the amount of disorder of a system. So we can look at conservation of energy in terms of this as well. Now, entropy is not conserved. Entropy is always going up. We'll talk about that in a second. But basically, when something heats up, the particles are going to move more. They're going to jiggle more. They might flow if they turn into a liquid. They'll bounce around the container faster. You have more what's called disorder. So as something heats up, the disorder gets greater, and entropy is a measure of that disorder. So as something heats up, the entropy grows. So second law of physics, or of thermodynamics with entropy, is the total entropy of a system that undergoes a change cannot decrease. Now we're talking the total. So if you put those ice cubes in water, the ice cubes are going to start to melt. So they will get more disordered, but the water will get colder. So it will get more ordered. So do those two amounts of entropy, the amount of entropy that the ice, gains because it's getting warmer, does that equal the amount that the water loses? It doesn't. So when you measure entropy, what you find out is the entropy of that system, the water ice system, would increase. So anytime there is a change in thermal energy, anytime something gets heated up, you're going to have an increase in entropy. Again, this goes back to the fact that no engine can be perfectly efficient. You're not going to get 100% efficiency. There's always waste. So there's always increased disorder as a result of that waste. So any irreversible process, you're going to have an increase in entropy, and purely reversible processes where things can go, back and forth with no energy added whatsoever don't really exist. They're purely theoretical, which is why the net entropy of the universe always increasing all the time. Irreversible process. What do I mean by that? Basically, friction pulls energy out of a system. Unrestrained expansion, you're going to have energy transfer as heat due to temperature, non-uniformity. You're not going to get a perfect system. It never, ever, ever, ever happens. So as a result of the fact that all processes are irreversible to some degree, entropy always, always, always goes up. So just keeping it simple, because the AP test does love conceptual questions about entropy. If something is heating, if heat transfers from one thing to the other in a real world, non-reversible process, the entropy is going to go up of the whole system. You might have, so we take a look in our picture, as the heat from the hot reservoir flows to the cold reservoir, the entropy of the hot system goes down because it's cooling down, and the entropy of the cold system goes up because it's getting warmer. But the total entropy of both put together always, always, always increases. So entropy, the amount of disorder of the universe or of a particular system, always increasing whenever you have a thermal process happening. And that's the end of chapter 12.